Okay, so our session's being recorded. Yes, Binyam is correct. So we are going to talk about optimization, but you've already seen some constrained optimization in calculus too. Like for instance, if you want to minimize the cost to create a box, but you want the box to have a certain volume, how big should the sides and the base be, and that sort of thing. Or what's the maximum volume of a box given this amount of material? How many recall those kind of problems where you had to maybe minimize or maximize a function subject to a constraint? Okay, Binyam's knows that. Solomon knows that. Yes, yes. And so of course here we're studying that too. Now that you learned about quadratic forms in section 7.2, we can talk a little bit about constrained optimization. So, okay, we start here at the beginning. So engineers, economists, scientists, and mathematicians often need to find the maximum or minimum value of a quadratic form in some specified set. Typically, the problem can be arranged so that x varies over a set of unit vectors, and the constrained optimization problem, this constrained optimization problem has an interesting and elegant solution. Okay, and then there's an example 6 that they'll talk about that is a very interesting problem. Okay, all right, so a requirement that a vector x be a unit vector can be stated in these different ways. And this is commonly used in applications where you require that the norm of your vector equal 1. Okay, that's required sometimes. And of course, if a quadratic form has no cross product terms, it's easy to find the minimum or maximum value of the quadratic form given that constraint. So for the first example, they start off by saying, okay, hold on, let me get, there's a little bit too much yellow here. Find the maximum and minimum values of this quadratic form, q of x equals 9 times x1 squared plus 4 times x2 squared plus 3 times x3 squared, subject to the constraint that the norm of the vector equals 1, or the norm squared equals 1 of the vector. So, okay, let's take a look at what they're doing here. They note that certainly, since x2 squared and x3 squared are non-negative, 4x2 squared would have to be less than 9x2 squared, and 3x3 squared would have to be less than 9x3 squared. Okay, so in other words, 9 gives like the biggest weight of the three coefficients, 9, 4, and 3. 9 has the biggest weight. So certainly the quadratic form would have to be less than or equal to 9x1 squared plus 4x2 squared plus 3x3 squared. And then that would be less than or equal to 9 times each one of those variables, well, the sum, 9 times x1 squared plus 9 times x2 squared plus 9 times x3 squared. Certainly that's true, but why would we want to write it that way? Because you can factor out the 9, and then the highest value the quadratic form would be 9, because you're requiring that the sum of the squares of the elements of the vector equal, I want to say this the right way, you're requiring that the constraint be held. And the constraint is that x transpose times x equals 1. Well, that's another way of saying x1 squared plus x2 squared plus x3 squared equals 1. Okay, so the maximum value of the quadratic form cannot exceed 9, okay, when x is a unit vector. Therefore, 9 is the maximum value of the quadratic form, okay, given the constraint. given the constraint. And we can also say, similarly, well, what would the minimum value be of the quadratic form given the constraint? What would the minimum value be? Absolutely, it would equal 3. Okay, so you have a minimum value and a maximum value for the quadratic form subject to that constraint. Are there any? Well, I know you're trying to absorb it here. Notice that, well, what would the eigenvalues be of, let me see here. The quadratic form, what would the eigenvalues be for the quadratic form? For this quadratic form up here, where there are no cross product terms. That's right, Solomon. It would be 9, 4, and 3. 9, 4, and 3. Okay, and so it's easy to see that the matrix of the quadratic form in this example has eigenvalues 9, 4, and 3, and then that the greatest and least eigenvalues equal, respectively, the constrained maximum and minimum for the quadratic form. Okay, and they make that comment, and the same will hold true for any quadratic form, as you will see. Okay, and so they have an example 2 here, where they have a 2x2 matrix. Well, first, are there any questions on example 1? All right, I want to just let me see here. I'm going to move forward here. I'm going to move forward to. I'm not saying it's just not a good example, but I just want to move forward to theorem 6. To theorem 6. Okay. Okay. And actually, I guess I do have to go back a little bit here because it relates to example 1 quite nicely. It can be shown that for any symmetric matrix, the set of all possible values of the quadratic form, okay, is a closed interval, and the minimum value of the quadratic form is equal to m, and the maximum value of the quadratic form is equal to capital M. And if lambda is an eigenvalue of A, then the eigenvalue has to fall between the lowercase m and the uppercase m. And the next theorem says that lowercase m and uppercase m are themselves eigenvalues of the matrix A. Okay, and they say just as an example 2. So I sort of intuitively felt this with example 1, but let's go ahead and look at example 2. Okay. So take a moment to read it. Take a moment to read it, and then I'll go through with it with you. Okay, so let me ask you, the quadratic form Is there any cross product terms to this quadratic form in example 2? Are there any cross product terms? No, because you have zeros off the diagonal. That's right, Solon. That's right, Robin. And so the quadratic form is going to be 3x1 squared plus 7x2 squared. And geometrically, this might be a little easier if you've had calculus 3. But if you were to graph this, this is going to be a paraboloid. This is a picture in figure 1 of what the quadratic form looks like geometrically. It's a paraboloid opening up. Now, in figure 2, they're showing the intersection of this quadratic form, this paraboloid, the cylinder x1 squared plus x2 squared equals 1. So the reason they have that cylinder there, x1 squared plus x2 squared equals 1, is because that corresponds to the constraint that the magnitude of the vector x equals 1. If the norm of the vector x equals 1, then the norm squared equals 1. And so x1 squared plus x2 squared equals 1 is the same as saying limit the vectors, limit the coordinates, so that every coordinate has a norm of 1. And the result is you get a cylinder. You get a cylinder. Okay, well, I want to be a little bit careful. You get a circle. You get a circle, right? x1 squared plus x2 squared equals 1. But if you raise the circle up and down, okay, well, in calculus 3, x1 squared plus x2 squared equals 1 is a cylinder. In 2 dimensions, it represents a circle in the x1, x2 plane. But in 3 dimensions, x1 squared plus x2 squared equals 1 is a cylinder. Because you're not saying anything about what z is. You don't care what z is. All you care is that the x1 and x2 satisfy x1 squared plus x2 squared equals 1. How many recall that maybe if you've taken calculus 3, that like x squared plus y squared equals 1 in 3-dimensional space is a up and down cylinder? How many maybe have seen that? Or remember that from calculus 3? Okay, and maybe some of you haven't taken calculus 3. That's okay. Hey, it's available in the spring, right? It's a really great course. All right. So what's happening is then the points, that red like band that they drew is points that are on the paraboloid, but points whose x1 and x2 coordinates satisfy that x1 squared plus x2 squared equals 1. And so you have all those points satisfy that. It's like, you know, if you pull your belt up, or if you pull your belt up, right? Your belt conforms to your body. Your body's like the cylinder, and you pull your belt up, it kind of looks like that, right? Okay, whether you're a man or a woman, right? You pull your belt up, it's going to look like that. And look at the coordinates of the lowest and highest points on the red band there in figure 2. The z coordinate is 3 for the lowest point on the band, and the z coordinate is 7 for the highest point on the band. Okay, and 3 and 7 correspond to the eigenvalues. They correspond to the eigenvalues, because we learned last class that when you have a quadratic form with no cross product terms, the coefficients of the x1 squared, x2 squared, and so forth are eigenvalues. So this then brings up the idea that indeed the that the lowest, the smallest value m and the largest of the quadratic form, the minimum of the quadratic form, and the maximum of the quadratic form are going to be corresponding to eigenvalues, and it's actually a great example 2. And so now this lends itself to theorem 6. Okay, so m is the greatest eigenvalue of A, big M, and little m is the least eigenvalue of A. Okay, and in fact, the value of the quadratic form is going to be that biggest value m, maximum value, when x is a unit eigenvector corresponding to m. Okay, a unit eigenvector, so you have to scale that eigenvector so that its norm equals 1. And then the value of x transpose, the value of the quadratic form is lowercase m when x is a unit eigenvector corresponding to lowercase m. Okay, so they give a proof, but I think intuitively I'm comfortable with that based on example 2. You're welcome to look at the proof, but I want to try to leave a little class time for you to work on on that new homework. So, but are there any questions so far before we move forward? All right, Kevin's good, Sega's good. All right, well, very good, very good. Then Christy's good. Let's go ahead and move forward here. Okay, so example 3. Whoops. Example 3. Here we have a 3x3 matrix, and we want to find the maximum value of the quadratic form subject to the constraint that the norm of the vector equals 1. And we want to find a unit vector at which this maximum value is attained. So by theorem 6, the maximum value is the greatest eigenvalue of A. And of course, when you have a quadratic form that has no cross product terms, theorem 6 is very intuitive. They prove it for more generally in the proof above. Well, I want to be careful here. They do prove it a little more generally, but we're just gonna go with what intuitively we feel is correct, okay, based on what we've learned. So, okay, the greatest eigenvalue turns out it's going to be 6 for this. So you don't have to get the you don't have to factor out the characteristic equation, because you can get those values easily using a calculator. Just graph the polynomial and find the roots, right? So given that, hold on here, let me go back here. The constrained maximum is obtained when x is the unit eigenvector for lambda equals 6. And so you're going to solve the a minus 6i times the vector x equals 0. Okay, and they have a little typo here. That 0, this 0 here, should be in bold, right? That's a matrix equation. Okay, so that should be in bold. And when they solve it, they get an eigenvector 1, 1, 1, and so the unit eigenvector is going to be 1 over root 3, 1 over root 3, 1 over root 3. Okay. All right. Are there any questions so far? Okay, it is. I agree, Benjamin. It is very interesting, and there are whole, optimization. I mean, I took a course that was all on optimization, and it's really fascinating material. And it's nice that we got to section 7.3 so that, hey, you could recognize this subject, and who knows, doing operations research, for instance, involves optimization. All right, so, well, you can have different constraints, Solomon. You can, and in fact, hold on here, one moment. I'm just looking at something from multivariable calculus after you asked that question regarding what are called Lagrange multipliers. One moment. Let me just, one moment. There's a reason I'm doing this. So, Binyam asks, can you have two constraints? You absolutely can. You can have two constraints. And in fact, in theorem and Lagrange, well, in multivariable calculus, they'll show that for Lagrange multipliers. But we're dealing with linear algebra here. So right now, today, right? So here's an example where you have two constraints. Two constraints. The norm of the vector equals 1, and the dot product of this vector x with u1, okay, and u1 would be the eigenvector corresponding to your maximum value, okay. If that is required to equal 0, okay, then the maximum value is the second greatest eigenvalue, and the maximum's obtained at the eigenvector u2. Okay, good. So my brother answered the phone, very good. And we won't worry about the proof now. Let's just go right to an example. But basically, I want to be careful what I say, but it essentially adding another constraint brings the maximum down. So example 4, okay, let's look at example 4 here. Here you want to find the maximum value of that quadratic form subject to two constraints, okay, and they are letting u1 equal 1, 0, 0. Note that u1 is the eigenvector corresponding to the greatest eigenvalue, lambda equals 9 of the quadratic form. Find the maximum value. So here's what they do. Here's the quadratic form, 9x1 squared plus 4x2 squared plus 3x3 squared. Okay. The 1, 0, 0. Hold on here, one moment. Okay, so x1 is equal to 0 because the only way that can happen, the reason that happens is the second restraint, for that to equal 0, it means that x1 has to equal 0 because the vector u1 is 1, 0, 0. So you only need, I mean, if in order for that to happen, the x1 coordinate from the vector x would have to be 0 because only 0, when you do the dot product, you're going to have a 0 times 1, right? Something's going to multiply that number 1 from the u1 vector. Well, it's going to have to be a 0 because the second constraint is x transpose times u1 equals 0. Okay, so this means then that x1 equals 0, and so the quadratic form gets broken down into 4x2 squared plus 3x3 squared, and the highest value that could be is 4. So the constrained maximum doesn't exceed 4, and incidentally, that value will be attained for the eigenvector 0, 1, 0, which is the eigenvector for the second greatest eigenvalue. So you see, it's like it's like the more constraints you put on the system, it affects what the maximum would be subject to the constraints. Absolutely fascinating. Absolutely fascinating. Okay, are there any questions on that? Let me ask you this. For example 3 above, okay, example 3, if you had the two constraints they mentioned here, these two constraints in theorem 7, and you use that in regards to example 3, okay, hold on, and incidentally, here's the characteristic equation factored out. What eigenvalue would you be using? What eigenvalue would be using? That's right, Solomon. You'd be using the second 3, because 3 is the second largest eigenvalue. Okay. And but are there any questions on that? I want to make sure that you're comfortable with what's being talked about here. That's right, Binyam. The amount of constraints that you want depends on the scenario and what you're measuring. That's absolutely correct. Absolutely correct. And a character, let's see. Noah says Noah says the critical points are the points where the gradient of the equation and constraints are. Okay, so Noah's talking about actually calculus 3 concepts, and yes, I mean I'm just I don't think so quickly. I don't think so quickly, but this is something I'd have to think a little bit more about, Noah, but you know, it'll be saved in the chat window. I'll have to look at that a little bit later and think about that. I'm always careful before you know, saying, you know, yes, that's correct, you know, or no, that, but the maximum optimization does come up in calculus 3, and it involves gradients, like the Lagrange multiplier method involves gradients. So I can see where Noah's coming from. Thank you, Noah. Okay, so let us see here. So okay, well, given this, we can go right to example 5 here, and they're just saying, hey, you know, if you had the matrix in example 3 and you had the two constraints, then yes, the second greatest eigenvalue would be lambda equals 3, and you would have to solve this augmented matrix to get the answer. And incidentally, this is one of the things I want to mention. I guess I'll mention it now on the exam. A few people lost not a lot of points, but a few points, maybe like 3 points, because every time they solved an augmented matrix, they would not like have the 0 on the right hand side. The augmented matrix would just, like that A minus 3i times the vector x equals 0. You know, let me like this here that I'm highlighting. Okay, some students would just row reduce the left part of that equation, a minus 3i. You know, they would times that vector x. They would row reduce the left side, but not include the 0, probably because they thought it was trivial to include the 0 vector. But it is an augmented matrix, and you have to have the 0 vector included in your augmented matrix. So just keep that in mind for the final exam. You know, I know, you know, hey, you know, you do enough of these and you kind of take shortcuts, but you don't want to take that shortcut because you lose meaning in the problem. But all right, that being said, this problem here, then you just normalize to get your U2 vector, and U2 will automatically be orthogonal to U1 because vectors correspond to different eigenvalues, and the maximum of the quadratic form subject to the constraint is 3, attained when x equals U2. All right, and I know it's going to take a little time to get comfortable, but you know, hopefully with enough examples, you'll be comfortable. Are there any questions so far? Hold on, did the ebook, okay, the ebook went, hold on, let me bring the ebook back. It kind of goes dead after a while. I don't know why, but it's okay. Everybody saw it. Did everybody see the example 5 that I talked about? Did that show okay? Hold on here. Okay, the ebook. All right, let me bring it back here. One moment. I think I have to go out and come back in. I have to. Hold on here. Let me bring it back. Probably got to pay a little money to make it not do that, right? All right, so one moment. I'm going back into section 7.3. Okay, there's example 5. Let me bring it back in the recording here. Okay, so this is what I was talking about. Example 5 related to example 3. And you have the 2 constraints here, 2 constraints. And so the second eigenvalue is your focus then. Second greatest eigenvalue is your focus. You find the eigenvector for that, and you solve the augmented matrix. And like I was saying, that augmented matrix, some of you on the exam, when you solve that to find your eigenvectors, you're just like some of you, not many, but a few of you are just doing the left-hand side. You're row reducing the a minus 3i part, but you're not including the 0 vector in your matrix, and that's not correct. You have to have it all in there, okay? It's just because it loses meaning without that. So just keep that in mind for the final exam. All right, the maximum value of the quadratic form subject to that constraint, those 2 constraints, is 3, attained when x equals U2. That's second eigenvector. The next theorem generalized. Are there any questions on that? All right. The next theorem generalizes theorem 7 and gives a characterization for all the eigenvalues of A. Okay, they omit the proof, But there's the big theorem 8. There it is. And it basically addresses the fact that all of these eigenvalues in the context of optimization, they have meaning based on a certain number of constraints. If you have 3 constraints, you're going to focus on the 3rd largest eigenvalue. If you have 4 constraints, you're going to focus on the 4th largest eigenvalue. And this concept is very important for future applications. One application is applications to image processing, to image processing. Okay, so what is that? What is that? Well, let me show you here. If I can, hold on here. I want to bring the, hold on. What I'm trying to do is go back here. I might have to, let me see if I can find it here. It's at the beginning of chapter 7, page 396. Let me see if I can just type that in. Yeah, image processing here. So they take photos below. They talk about principal component analysis, and again, that relates to optimization. But they take images here, and images from 3 spectral bands are shown. Okay, so take a look here. 3 spectral bands. Okay, I don't want to get too complicated, but here's the idea. Okay, when you have an image, okay, how many know, just from knowing about computers and graphics cards and things like that, that very detailed images require a lot of data to have a very detailed image? Absolutely, absolutely. Well, sometimes what you can do is you can, thank you, Maisha, thank you. Let's see. Maisha, Devahar, Robin, Binyam, yeah. So sometimes what you can do is you can break up the information for an image into important components. Okay, and that's called principal component analysis, and optimization is needed for that. So what they do here is they have the image of this valley, and they have, like in part D, they have principal component 1, 93.5%. So the first component related, and again, we just don't have time to cover it, but it's in section 7.5. You're welcome to look at it on your own. Applications to image processing and statistics. But you see, you could use a portion of the information to capture the image. Like, in other words, the first component of the data captures 93.5% of the image in part D. The other 2 components, principal components, the principal component 2 and 3, don't cover that much of the data. In other words, their contribution to the entire image is not that much. So you might be able to get away with just using principal component 1 for getting a decent image. Okay, that's how I like to think of it. That's how I like to think of it. But of course, if you, and again, you know, it relates to optimization. Okay, so, you know, I think if you go ahead, let me just see here. I'm just seeing if there's anything else I can. Yeah, principal component analysis can be applied to any. I'm looking at 7.5. I'm just reading kind of a little bit of the intro, but principal component analysis can be applied to any data that consists of lists of measurements made on collections of objects or individuals. Loosely speaking, well, I want to be careful here. Essentially, what you're trying to do, you have multivariate data and you're trying to reduce the dimension of the data. You have the data for an image or some multivariate data, which could give an image, for instance. And not all that data is important to understand the image. Like, for instance, this valley that they're showing here, principal component 1 captures 93.5% of the image. Principal components 2 and 3 cover less. So the idea is you're just trying to effectively, you have all this data coming at you and you're trying to sift through the data and find the most important component of the data. And then there's a second most important component of the data, and so forth. That's what you're trying to do. And it's absolutely fascinating. How many think this is a pretty fascinating idea here? Christie's, I think that's a happy face. I don't know, but kind of Ryan likes it, Robin likes it, Binyam likes it, and so Devahar likes it, and so, you know, it's really a cool subject. And I wish we had like a linear algebra second part of the class, because then we would get into this. But that being said, let me just now, one moment, let me go back to the page I was at. We were in section 7.3. And 7.3, I'm going to page 414. They have an example here where they talk about what's called a feasible set. How many have heard of a feasible set, like when you would have like lines and inequalities, and you would have a feasible set that's the intersection of all the inequalities? It was called a feasible set. Does anybody recall that, maybe from college algebra, feasible sets? You would have inequalities. This makes more sense if you, Devahar's heard of it. Well, I'll tell you what. I think what I'm going to do, example 6 is an interesting problem, but I think you're welcome to look at example 6, okay? And it's another application of optimization, just like the principal component analysis was. But I think on that note, I'm going to stop, because I want to give you some time here to work on this new homework. So are there any questions before I stop the recording? Okay, let me stop the recording.